Hi there, this is Mr. Ambrose's video for class on Monday in Algebra 2 Trig. Before I get started, I have some good news to share with you guys, and unfortunately some bad news. The bad news is that the next chapter that we're going to look at is still going to be in trigonometry. But the good news is that this is going to be the last chapter that we examine in trigonometry this year. Wow! I could hear all the loud cheers going on as I'm sitting in my conference down in San Antonio. Alright, this video is going to examine specifically the area of a triangle. Now you may be saying to yourself, Mr. Ambrose, I already know the area formula for a triangle. That's equal to 1/2 base times height. But there is another formula that we have to actually find the area of a triangle, and that's going to involve some trigonometry. Before I go and derive this formula, I want to examine the sine of an angle and the sine of a supplement. And to do that, I want to look at the unit circle that you see there on the screen. In particular, if we consider an obtuse angle and call that angle theta, where that angle terminates on the unit circle, I'm going to label that point there x, y. Through our work this year with the unit circle, we know that if we were to examine the sine of theta, that's going to equal y. Now, we also know that through the year, when we sometimes try to examine the sine of any angle, one of the things that we found was its reference angle. And in this case, the reference angle would be that distance from the terminal side of our angle down to the negative side of the x-axis. So I'm going to call that reference angle little r. If we were to take our angle theta and add that to angle r, that value would actually be equal to 180 degrees. So this would mean that angle theta and angle r are supplementary angles. Now, I'm going to draw another unit circle, and I'm going to now only draw the terminal side of our angle theta. We know that that ends at the coordinates x, y. I'm going to put the reference angle r there, and what I'm now going to do is I'm going to reflect that particular terminal side about the y-axis. Now, because of our understanding of the circle, we know that there's lots of symmetry here. So, the point on the other side of the y-axis would have basically a negative x value, but the exact same y value. In addition, the reference angle r should be the exact same angle over there in that first quadrant. So, if we were to actually evaluate the sine of angle r, that should equal y. And since both angles theta and r are supplementary, the sine of angle theta equals the sine of angle r. And so supplementary angles have the exact same sine value. Okay, so there's just one more thing I have to go over with you guys, and then we can go about deriving the area formula for a triangle. You'll see on the screen two different triangles. To the left we have an acute triangle, and to the right we have an obtuse triangle. Both triangles are the triangle ABC. And as you've seen from years past, the angles of the triangle we label with an uppercase letter. The sides of the triangle, well, we could perhaps call one of the sides of each of these triangles the side AB. But instead of calling that side the side AB, I could also call that the side lowercase letter c. It's a lowercase letter c because that side is opposite the angle c. So the other sides of my acute triangle, well, to the left I can call that lowercase letter b because that side is opposite the angle b, and the last side I can call lowercase letter a because that's opposite the angle a. I can do the exact same thing with my obtuse triangle and label each of the sides with their respective lowercase letter. Alright, so now we're ready to go about deriving the area formula for our triangle. We'll begin by utilizing the area formula we already know, that the area is equal to 1/2 base times height. And in my acute triangle, I'll draw my altitude there from C so that I have a height of the particular triangle. And I'll label that altitude H. So in our area formula, we would have that area is equal to 1/2 the base, which how I set it up would be C, side C, and height of H. Now, this is still nothing new, but the idea is, or what we're going to go about doing, is I'm going to try to eliminate this H and replace it with either the sides and or the angles of our triangle. And the way that we can do that is when I constructed the altitude of the acute triangle, we now have two smaller right triangles. And specifically, if we focus in on the right triangle on the left-hand side, we could use trigonometry to evaluate the sine or the cosine or any of the angles in that particular triangle. In particular, if we calculate the sine of angle A, the sine of angle A based upon that right triangle would be equal to H over B. If we then use that to solve for our altitude H, we would get that H is equal to B times the sine of A. And then using this expression for the value for H, we can finish off our area formula and get that the area is equal to 1/2 side C times B sine A. And this is the way that we can calculate the area of our triangle that involves some trigonometry and only involves in that area formula the sides of our triangle and its angle. Okay, so now I'm going to show that the formula will be exactly the same even in our obtuse triangle. And so I'll begin by drawing out another altitude from C, and we'll also start off using our area formula that the area is equal to 1/2 base times height. Into that area formula, we can plug in lowercase letter c to represent the base side of our triangle, and the altitude that I just drew, I'll still call that H. Now, just like with the acute triangle, I will then go about trying to calculate the sine of angle A. And I'm going to do that by actually utilizing the smaller right triangle that we have there on the left of our obtuse triangle. Now, the only problem with attempting to try to do that is that the angle A is not in that smaller right triangle. It's only in the obtuse triangle. But if I look at the angle there to the left of angle A, I'm going to call that angle little r, because that angle r and the angle A are supplementary angles. And so, as we just saw, the sine of A, therefore, should equal the sine of r. And using that smaller right triangle, the sine of r should equal H over B. And as we had with the acute triangle, if we then just go about solving for our H, we get that H is equal to B sine of A, and that is exactly the same thing that we got with our acute triangle, so we indeed get the exact same formula for area. So we now have our area formula for a triangle that involves trigonometry. Specifically, we have the area is equal to 1/2 sides B times C times the sine of angle A. But note that the angle A is included in between the sides B and C. And so, because of that, we could rewrite our area formula in two other ways. But although we're using different letters, the relationship is pretty much the same. In the second formula, the angle C is included around the sides A and B. And in the last formula, the angle B is included around the sides A and C. The derivation of those second and third formulas could be done in the exact same fashion as what I showed you. So this concludes this video. I apologize that it slightly went over the 10-minute mark, but hopefully it will help you completing the problems that you'll see in class on Monday. Thanks for tuning in, and I hope you are enjoying your weekend.